Hi, everyone, and thank you for joining our webcast today, Affectiva AI Technical Deep Dive. My name is Ashley McManus. I am the Director of Marketing at Affectiva, and I'll be your host today. With me, I have Jay Turcot, our Director of Applied AI, who is leading our team of machine learning researchers and focused on bringing to market our core emotion technology. Before we begin, some housekeeping items. You can tweet during the event using the hashtag EmotionAI and tweet us at Affectiva. If you have any questions during the event, please write them in our Q&A section located in the bottom right of your screen or ask us in the chat box. Technical difficulties, please send us a message through WebEx or email us at events@affectiva.com, and we will do our best to work with you to resolve the issue as we have quite a few registrations today. Also, please note that we are recording the webcast and will make the recording available to registrations before the end of the day. So before I hand it over to Jay, a little background on who we are. Affectiva is a MIT Media Lab spinoff and is the pioneer in Emotion AI, the next frontier of artificial intelligence. Our patented AI platform uses computer vision, audio analysis, deep learning, and detects complex and nuanced human emotions and cognitive states from face and voice. Affectiva is working with leading OEMs and Tier 1s on next-generation in-cabin sensing, specifically around monitoring of driver state, such as drowsiness and distraction, to improve road safety, as well as measure occupant mood and reactions to optimize and personalize transportation experience. This is all powered by the world's largest emotion data repository of over 6 million faces analyzed across 90 countries, amounting to more than 50 billion data points. And now I'll hand it over to Jay. And again, as Affectiva's Director of Applied AI, Jay guides our data acquisition and annotation strategies and development of new deep learning techniques to improve the robustness, speed, and accuracy of our emotion models across vision and speech modalities. So without further ado, I'll hand it over to Jay for his technical deep dive presentation on Affectiva's core technology.
Great. Thank you for that. Ashley, am I coming in loud and clear?
Yes, you are. We hear you.
Okay, great. So let's get started because it's got a pretty jam-packed deck, and I know there's a finite amount of time. So again, thank you for the great introduction, Ashley. My name is Jay Turcot. I do head the research team here at Affectiva, and what that means is everything from the data acquisition, the annotation, as Ashley mentioned, all the way through to getting these models into our products, our core SDKs, APIs that those of you who are listening in are hopefully already familiar with. So what does it take to actually go from, to have these SDKs do what they do? That's what we want to talk about today. So to contextualize this a little bit, what I want to do is frame it in the automotive industry, an industry that's getting a lot of attention now as being an applied, a use of AI, computer vision technologies especially. So let me give you an overview of the what, the problem that Affectiva is addressing in this automotive space context. So Affectiva, what we're trying to do, or what Affectiva's technology is striving to do immediately, is build, the next generation sensing platform. So this is a platform that could continuously monitor in-cabin occupants' cognitive and emotional state, and we could do that for a number of reasons: to ensure their safety or to optimize their driving experience. For example, this platform could be used to enhance the next generation driver monitoring system in semi-autonomous cars to enable smooth control between a driver and an autopilot system. So to do that, where Affectiva's got our core technology, our core depth, is really understanding and sensing people. And so when you extend that sensing of people's emotional and cognitive states from looking at their face and voice into the cabin, what we want to do is build a platform that takes more context, even their body posture, potentially what's going on outside the vehicle, inside the vehicle, the time of day, for example, and just fold that in to build an improved estimate overall, either be it their emotional state, anger, surprise, their cognitive state, whether or not they're distracted, or potentially drowsiness. Underpinning all of this technology or all of these capabilities is the same core technology background, which is what we're going to be digging into today. So before we take a look at the details, let's just take a quick look at what the output of all this effort looks like in action. All right.
What's the youngest star you've dated?
I don't know. No, you know,
What's
it has to
your
be
cutoff?
legal.
I'm
Not that kind of girl.
saying
I'm a
you're not.
relationship kind of girl.
I'm not saying you're not. What's the most romantic thing you've ever done?
Most romantic?
Yeah.
All right. So in that example, we saw two people in a car just having a conversation. And of course, this conversation was an emotional one in nature. And all the while, the car could be sensing their emotional state, understanding what's going on inside the car, and adapting accordingly. This could be a single driver by themselves, listening to music and reacting to the music, or it could be a driver at the wheel on a more cognitive state, starting to fall asleep and showing other facial signs, facial cues of being drowsy. So underpinning all of this is what Affectiva calls emotion AI, which is just the understanding of an occupant or an individual, their emotional cognitive state. Now, in machine learning in terms, emotion AI is really a complex problem. So my background primarily is from computer vision and machine learning. And what makes emotion AI a complex problem is a number of factors, and I'll go through each one. One, it's multimodal. So human emotion, it manifests in a variety of ways, not just by facial expression, where Affectiva first SDK worked, but also in the tone of your voice, and you could factor in other contextual signals, body language, for example. We've recently extended our analyses to include the capability of analyzing audio as well. In terms of a classification problem, there's many different facial expressions that manifest. Facial muscles can generate hundreds of different facial expressions of emotion. In speech, have a variety of different dimensions to analyze, pitch, resonance, to melody, to voice quality. The problem you're trying to solve is one that is really highly nuanced. What you look at here is the difference between individuals, the difference between a young baby to a teenager to an elderly woman and a baby boy. Those differences span age, gender. You'll see differences in facial appearance as well as in their voice that we need to effectively ignore and pick up on really subtle cues, the slight change in intonation in the voice, the subtle curl of the lips for a smile. And that's what we need to detect while ignoring these massive differences caused by individuality. Looking at time, I'll try and go through this quicker. Additional things, there's temporal lapse. The temporal sequence matters. Emotions can be non-deterministic. That's where the context comes into play. The same expression under different contextual environments has been shown to be interpreted differently depending on the body language or what's occurring around. We've seen before in past work in automotive that people can smile because they're frustrated. Actually, they're almost laughing at the ridiculousness of the situation. And of course, as we mentioned in the automotive preamble, that we want to go beyond emotions. Really, this technology can analyze not just emotional states, but also cognitive states. To create and actually execute this requires massive data and increasingly more context. So I think it goes without saying that machine learning is a must. No one is going to pursue this without using machine learning. But what does that actually mean? Well, any machine learning approach, and very specifically Affectiva's machine learning approach, relies on 4 strong pillars. The data you use to train the models, the algorithms that you develop, these new machine learning models that are analyzing the data, parsing it, storing that information to be then deployed, the infrastructure you use to train and test all of your models to make sure that they are working accurately in the environment where you're planning to deploy these models, And of course, the backbone of all of this are the group of people. So I'm going to dig more into the data algorithms and infrastructure at Affectiva today. So going back to that example that we saw earlier of Jennifer Lopez in the car, what was actually happening there? Well, what we were doing was real-time facial expression and emotion analysis. And there was a number of different components that work together, and we'll see the actual models that go into those. First, a deep learning face detector has to localize and track all the faces present within a video or an image, a video feed. Then our deep networks analyze the face, the actual pixel, the information stored in the face, the shading, the wrinkling, the facial landmark positions, etc., to classify the facial expressions of emotion. And currently in market, we have 20 different expressions that we could detect, 7 different emotional states. The current SDK also, to demonstrate that we do more than just the prototypic emotions, actually exposes 13 different emojis to show how it picks up all the facial movements. As well, you could do other targets where you estimate age, gender, and ethnicity. And the great thing about this is that it has to work on any standard webcam. Right now, we're doing work to extend that and generalize that into near infrared, which is a very common camera in the automotive space. Now, on the audio side, it's a very similar pipeline to what happens in the face. Rather than being visual information now, it's the raw amplitude signal. So first, a voice activity detector detects when a person is speaking. Then we take that raw input audio and feed it through a deep learning network to do simultaneous feature extraction and classification in order to produce estimates. The current system starts analyzing after 1.2 seconds of speech and continuously produces emotion estimates while people speak. Now, before we dig into the actual algorithms, one thing that's worth noting is that Affectiva, one of the targets of the research team, is to have our models run in embedded and mobile devices. And we believe that's important for a number of reasons. The first is privacy. Not every individual or every corporation is going to be willing to share a live stream of data of either video or audio back into the cloud for server-side processing. You want to, as much as possible, keep all that computing on the edge, on their actual device, so that they retain their data. The second, it needs to be real-time. So on-device models will be very low latency. Everything you need is right there on the device, computing estimates directly as close to the sensors as you can get it. And finally, it works offline. If you want to have a technology that's deployable in a vehicle, in a mobile device, you want this technology to ideally work despite there being a lack of connectivity, so that whatever you're doing downstream, whatever use case you're enabling, continues to work even when the device is offline. So let's start digging into the individual pillars that I spoke to earlier. The first is data. Well, before you could pursue any kind of development of advanced machine learning models, you need a data strategy. In terms of the automotive space, what this means for Affectiva is we have a number of different sources of data that we pull together in order to get drivers in car in order to feed our labeling team and our models. We have spontaneous occupant data, and what we did there are we have driver kits that we actually mail out to individual participants that sign up, where we collect naturalistic driving data over the course of large numbers of individuals over many weeks. And this is just people driving in day-to-day environments. We have data partnerships, and where we look to join forces with other organizations working on similar or related problems, and try to set up data partnerships where we get access to the data in order to improve the overall quality, especially in their use cases. In certain cases, we do simulated data as well. Data that requires potentially specialized hardware to gather accurate ground truth, either a multi-camera rig to collect simultaneous synchronized video of an individual from multiple viewpoints, or if you're trying to set up a situation where you're either inducing an emotional or cognitive state that is either sparse or rare in the real world, or could be dangerous to do in the real world. There will be some amount of simulated data collection that will be required. Ultimately, though, it's important that when you evaluate these models, it's always evaluated on that spontaneous real-world data. So just to give you an idea of some of the data that Affectiva has collected to date, you see it includes people going about their everyday driving tasks from a multitude of camera positions. It's both near infrared and RGB, which is important for allowing us to train and refine our models, both RGB, but also the near infrared to transfer what we learn from the RGB signal to near IR, as well as understand our performance in near IR. It includes people that are emotional, that are spontaneously drowsy, where again, people drive and go through a variety of emotional states. And this is all present in our data that we've collected to date. This occurs just from people naturally driving. All right. And so just to give you an idea of the data that Affectiva has built up to date, our data we've collected through all of our various use cases and applications over the years since Affectiva has been around spanned 87 countries. In total, we have over 50,000 hours of audio-video data with 6 million faces analyzed across a wide variety of countries. In the automotive space, we've collected 1,100 hours, and both of those data sets are growing steadily. We're getting 200 hours a week from in-market partners, and our automotive data collection is ramping up and is currently at 100 hours a week of data that's flowing in. You'll notice that the top countries, when you group this data by country, the top 10 countries in the world that we've pictured, or the top country we've pictured here, I forget the exact number, are scattered around the world. We're not, Affectiva isn't an organization, though we're based in the US, our data is not. It comes from a pool of global data, which is really important when you're trying to develop models that are meant to be deployed globally. Now, onto the algorithms. Given all this data, what are we actually using to process, ingest, train, and learn from this data? Well, obviously it goes without saying, I think these days, that it's a deep learning approach. Now the question is, why is deep learning? You know, for those listening in that are not familiar, deep learning is an area of machine learning in which you use large and extremely complex neural networks. This has been a hot topic in machine learning ever since around 2012. Its recent popularity goes back to 2012, where a team of researchers at the University of Toronto showed, groundbreaking performance on a object recognition challenge. And they basically blew the competition out of the water. Prior to that, machine learning was centered more around support vector machines, random forests. What deep learning was capable of was producing better accuracy than had been achieved before, and that was done through ingesting large amounts of data. So really, deep learning, the core fundamentals of it have been around since the 70s, neural networks. But where it's really made a breakthrough has been the ability to train these networks off large amounts of data, for these networks to become higher capacity, for GPUs to come into prevalence. And I'm sure everyone's seen now NVIDIA and their hardware, how it's exploded in recent years, partially and thanks to this explosion in machine learning and specifically deep learning. And so a large number of things came together in the 2010s to really unlock deep learning. And since then, lots of people in machine learning have justifiably switched gears into deep learning because it's proven itself to be a really, really great approach. Now, Affectiva is particularly interested in deep learning. Well, it allows the modeling of more complex problems with higher accuracy than other machine learning techniques. It allows for this graceful end-to-end learning where you go straight from the raw data directly to your target of interest. Care has to be taken in designing the architectures and feeding it the appropriate data, training it the appropriate way. But once that's been done, some of the applications you've seen in deep learning have been almost, I hate this term because in machine learning there's no such thing as magic, but to a layperson, it seems magical what these models can do. And also deep learning, it's not to say deep learning is just a single technique. It actually refers to a variety of techniques that solve a variety of problems: classification, segmentation, temporal modeling, localization. These are all solved with deep learning. So one of the roles of the research team at Affectiva is really to explore the different architectures that make up these models. Now, what do I mean by deep learning architectures? It's the specific sequence of layers, the size and number of layers that go into the model, which are then trained from your data to produce these predictions that you could use. Now, as I mentioned before, one of the focuses of Affectiva's technology is we want it to run on device. We want these models to not only be accurate, we want them to run fast with a low CPU memory footprint. We may not have access to specialized hardware by deploying to these embedded or mobile devices. And so we need these models to just be extremely compact, extremely fast. And in order to do this requires more than just slapping together a standard CNN and pumping data through. You need to try and break down the problem into, cascade the problem into quicker estimates that can then be fed into downstream steps. You end up almost creating more complexity in order to pursue the most efficient way of learning or solving this problem possible. So here we use deep learning for a variety of techniques. We use it for object localization and tracking. In specific, that is our face detector, landmark detector, and tracker. We use it for multitask, multi-class classification regression, where we simultaneously and jointly estimate what's occurring on the face. And all the while we're experimenting with different architectures and exploring this accuracy speed trade-off. So architectures that are already in our SDK release, obviously we use convolutional neural nets for image understanding, as well as region proposal networks. In our temporal models, we use convolutions with recurrent neural nets on top to analyze the temporal sequence of information, be it audio amplitude in analyzing the voice or a sequence of frames in a video, as well as LSTMs, DRNMFs as well. Now, it's important to note that there's a lot of research going on here where people tend to, for the purposes of comparison, use the same networks to show either the contribution of their individual idea or to try and push the best network possible, or in part because a lot of research out there doesn't have sufficient training data to train from scratch, so they use these models that have been pre-trained and try to refine on that. We're not using off-the-shelf networks. What we need to use are networks that meet our criteria, that solve our exact problem. And so our focus is really on designing different architectures, different layers, different losses to really help our models learn our task, the Motion AI task, as efficiently as possible. So as an example, what does that mean for our current vision pipeline? Well, as I mentioned before, the vision pipeline consists of a few steps. There's face detection, and that describes a machine learning problem, is given an image, detect the faces. So here we have a region proposal architecture where we have some shared convolution, a region proposal network that looks for candidate regions of interest where there might be a face present, and ultimately a classification, a decision that's made, yes or no, I believe this face is present. There's a face present there. Now, for each of the faces that we detect, we then have to do this per face analysis. First step there is landmark localization. So given an image in a bounding box, can you detect and track the landmarks? And this is an even more efficient step because here we're first trying to refine the landmark positions. So by landmarks, I mean the eye corners, the mouth corners, the chin tip, the tip of the nose, for example. We want to localize these because that gives us a more fine-grained estimate of where the face is located, the orientation of the face, the scale of the face in finer detail. And we could also solve this problem iteratively from frame to frame very quickly, which again, saves us the computation of running this face detector on every single frame. Ultimately, we produce the refined landmark positions as well as a confidence that we're tracking accurately. From there, we can extract a clear view of the face, a face image, which is then fed into our downstream facial analysis. Because we've isolated the landmarks, we can correct for rotation here and make the face upright. We can also correct for scale, which again simplifies the task that you're asking the downstream facial analysis to perform, which lets you create a smaller, more efficient architecture there. And so this, digging into what these look like in a little bit more detail, these are just example architectures of what these potentially look like. And when you talk about deep learning, it's really this stacking, this cascade of individual layers, where we have a shared convolution layers that go into a region proposal network where they produce scores and bounding boxes. We then look for just a small finite set of the best candidates, which are then used to feed a confidence score to give the final box, refine the final box position, as well as the confidence of the face. In the landmark regression, we do a rough initial preliminary landmark regression followed by a fine-tuning of our fine-grained landmark estimation, as well as simultaneously producing the confidence of the face, as well as other measures. Our downstream facial analysis is actually a shared pipeline where we process that normalized image, we process it through a series of shared convolution layers, and actually only at the end do the networks split into the expression and emotion classification. And this is because it best allows us to leverage all the data we have, where you might have data where you have emotion labels but not the expression labels present, or vice versa. We're able to train a single network that leverages all the data we have available, including data that's partially annotated with missing labels, to ultimately get as robust of a model as possible. Now, on the audio side, for some targets, we use simpler convolutional neural networks, where here, instead of convolving over pixels, we convolve over the amplitude of a sliding audio channel in order to, for example, predict gender. For more complex targets that might require more temporal context, more information beyond what we see in that short window, we'll use RNNs, recurrent neural networks. And obviously, recurrent neural networks refers to a family of architectures in and of themselves, and we experiment with a bunch of different ones. For example, one of the ones we've developed here at Affectiva, one of our researchers, is called the Dr. NMF, which is for non-negative matrix factorization. Ultimately, unlike conventional RNNs or deep learning networks in general, this Dr. NMF is based on an interpretable statistical model of the data, and the result is that we get faster training, deeper introspection, and easier improvements to the network architecture. And at the end of the day, what really matters is the Dr. NMF architecture performs better on a task, for example, audio source separation, than the equivalent state-of-the-art RNN when we train with less data. So one example of where this all comes is comes together are some results that I shared at GTC 2017. So about a year ago at last year's GTC. In the pursuit of trying to get on-device performance, in trying to take these architectures, these pipelines, we wanted to, again, try to find the most efficient models as possible. Now, that does mean that there will be a decrease in accuracy. With infinite resources, you push the upper limit of accuracy, and that is, to an extent, what large groups of academic researchers are pursuing. They're trying to push, and rightfully so, trying to push the upper limit of accuracy. What we're trying to do is find a better balance. What we're looking for is model efficiency. So one common architecture that's been around for a while, VGG16, is from the Oxford Visual Geometry Group. That's around 31 gigaflops in computation, that top bar. On a task, we tried using the VGG architecture just as a baseline for what one of these large architectures could achieve, and then compared them to some of the architectures that we were experimenting with internally. And overall, we found less than a 1% drop in accuracy for models that, that top plot's a log scale, for models that ran nearly 10,000 times faster or had 10,000 times fewer operations. And so really, when you're looking at taking a model and deploying it onto to have it work offline, deployed onto a device, would you take that less than 1% drop in accuracy? Absolutely. So another thing that's worth discussing when it comes to training models is bias. This is getting a lot of attention these days. This is something that Affectiva has been aware of for a while as we roll our technology out globally. And one thing to share is that from our global data set, we do find that we have a diverse data. Being able to measure and describe your data in this way is an important part of what it is that we do. Now, how do you take this and avoid bias? Well, there's different approaches you have to take. It's a really nuanced and difficult topic, but ultimately the goal that you're trying to do is you're trying to prevent overfitting. Overfitting in use cases where you accidentally learned a co-occurrence, a correlation that was inherent in the data, but that isn't necessarily reflective of how you want this model to behave when you deploy it. So before training, what you have to do is analyze the data and the statistics involved and try to identify possible sources of bias. During the training, you could mitigate this through different training approaches, sample selection strategies, weighted sampling, carefully constructed losses. But ultimately, what's important is at the end of the day, you test the performance across these same demographic splits or use cases and just make sure that you understand how the model behaves and try to use the feedback you gather there to iterate in the future. So the last piece I'll touch on, and I'll try to go through this a little bit more quickly, is the infrastructure. So deep learning that was unlocked, mid-2000s, what deep learning gave us were these extremely large, extremely complex models and the ability to train them. But one of the things that deep learning did was typically these models require large amounts of data in order to achieve their state-of-the-art performance. By and large, deep learning is still a supervised classification problem in which for every bit of data, you have a ground truth, a known correct answer, be it human-generated, estimated via machine, etc. The training of a deep learning model is still a supervised training task. Obviously, we're exploring areas where we could extend that to leverage not just data that we have that's annotated, but all of our data. So there's that area of research where you go semi-supervised, even unsupervised learning. So Affectiva, an important component of our enabling deep learning is this data infrastructure we have. So on top of our raw data, we have infrastructure to scalably process with prototype classifiers and mine our data for moments of interest, extreme head pose events, rapid head movement events. And what we do is we use this data mining to feed to weekly annotate our data and to feed our annotation team, who then looks through the data and tries to, and annotates it for expressions, emotions, whatever it is that their annotation task is. The key here, though, is that you want to use your annotation resources efficiently, because ultimately annotation, these models require annotated data, and you want as much diversity and as much representation in the annotated data as possible to unblock both supervised and semi-supervised learning. So what does our annotation infrastructure look like? Well, it's all in-house. We have multimedia video annotation that allows labeling of frame-by-frame moments down to the individual video frame for onsets and offsets of events, moments of interest. We have a separate annotation tool for doing facial annotation, so where the position is and metadata about these spaces, as well as a third for annotating facial landmarks. The annotation team are full-time Affectiva employees, and they're all facial action coding system trained. And one of the things we hold true at Affectiva is we always use multiple annotators. And this is a way of preventing not the kind of bias we were talking about before, but preventing individuals, single individuals' perceptions from dominating your training data. You want to ensure consistency and agreement between your annotators, and you need to have multiple annotators to achieve that. So ultimately at the core, the infrastructure looks like ultimately first our multimodal data collection, where we have through our partners, through our own direct data sourcing, through direct targeted experiments in lab data sets, we have the ability to collect large amounts of data. We have our data processing, data mining infrastructure, which ultimately feeds as part of our overall data labeling infrastructure in order to provide the human ground truth on the emotions from the face, from the audio observed by a large pool of individuals. We then have training and testing infrastructure to allow for large-scale experiments, parallelization of different experiments, trying each of these modeling tasks. And finally, we produce these models, these candidate models, that we then evaluate on our spontaneous real-world data in real-world use cases, with all the environmental noise, subtle, spontaneous expressions, and that's how we benchmark our ultimate algorithms. Because it's very important that even if your training data might come from various sources, you need to test and evaluate your model in the use case, in the situation where you're going to deploy it. As we are using various transfer techniques to shift our models that were previously learned on RGB images to work in near IR, we of course will be annotating and have annotated near IR data for the automotive in-car use case to act as the basis, the evaluation, the benchmark on which we measure the performance of our models for that use case. And ultimately, when they meet the bar, when they pass, when we have a model that we like, then they get integrated into our SDK API products. There's a whole team dedicated towards making our SDK run in a variety of environments and to make sure that these models, once we ship them, are available across different devices, access through clean platform, clean APIs that are, tuned to that specific platform. Finally, the end, all of this really comes together. All that infrastructure flows through to allow for rapid development, which is a combination of research expertise, domain knowledge, data. So as an example here, looking back at 2017, one of the things we did was start exploring a new model in speech. And at the very first prototype, we used public data sets just to say, hey, how are we doing on this problem with just a basic model using a deep learning technique. And over the course of 3 months, through a combination of trying out different architectures, adding in more proprietary data, as well as adapting the training process for feeding this deep learning model, we saw model improvement rise really quickly from a 0.66, which again is not amazing, but was what you would get if you just took an out-of-the-box architecture on an out-of-the-box data set. and push that up to 0.83 over the course of 3 months. Now, obviously, we're pushing beyond that to make these models robust to real-world noise, in-car, all sorts of distractors. But really, that's the key, is that this modeling approach is not just a single pass through where you label some data, do some modeling, get some results, ship a product. That's a single cycle, but that's a cycle that needs to happen continuously, over and over, and continuously adding more data, refining your models, and pushing out improvements. And so making sure that pipeline is efficient is really important when it comes to model development. Not every model you produce will be a release candidate. Not every model you produce will make it into the product, but you need this rapid experimentation cycle to continue to drive innovation internally. So, well, what comes next? I'm only going to touch on it at a very high level, but ultimately you heard of what it is in the preamble. As we start looking at automotive and we start building out new technologies in automotive, we really want to build this multimodal system capable of combining multiple channels to detect more complex affective states. The crux of that is really we want to build artificial emotional intelligence. There's a lot of things happening. There's a lot of machine learning happening in the car, in the environment. We want to be the people that understand through observing people what that means. So a coin termed, unfortunately not by myself, but I actually do like it. We want to go beyond the basic emotions and start looking at what we call people analytics. Can you do things like measure distraction, drowsiness? Because fundamentally, at the core, it's the same. It runs into all the same challenges that emotions would run into. What you'd see in terms of being able to estimate and measure distraction, drowsiness, for example. Going beyond individuality is personalization. Right now, our models are trained across a large number of unique individuals from diverse demographics, but you've seen in ASR that personalization yields improvements there. We believe that there's opportunity to allow for personalization of our models as well. We're starting to explore multimodal with both face and voice, but ultimately we want to push multimodal to include other channels. There's more than just these passive observations of you. There's contextual information. There's what was said if you're in a conversation. There's a lot of information that really needs to be pulled in order to get as accurate of an estimate as possible. And of course, all of this requires data, so we want to continuously explore methods that let us leverage all of our data, specifically semi-supervised, unsupervised techniques. And as part of that, as an extension of personalization, are looking at different ideas on how to actually get those individual personalized model updates and try and learn and improve our core models from our on-device models in a way that respects people's privacy. So that's kind of a snap vision of what I see coming in the future for Affectiva's research organization. With that, I do know I ran a bit over time, but we still have some time for questions.
All right, awesome. Thank you, Jay, so much for the presentation. We have quite a few questions coming in, so I'll field a few that we have time for. And reminder, if you do have a question, use the Q&A chat box on the bottom right of your screen, and we'll answer them if we have time. Okay, so the first question is, where does the ground truth of the real-world data come from?
Sure. So that, as I mentioned, we have our annotation team that is there observing these individual reactions. So in all cases where we have these data partnerships, I just want to preface that all of this is opt-in, that people are aware that they're being recorded, that their data is being used to train and improve our technology. And so those videos where we do have access to that raw data are edited by our in-house training team. We've done through our in-house data collection, we've done some other validation work where we will try and induce emotional states just to get a strong prior on the actual emotional state of interest. to help drive the verification. But ultimately, the ground truth for this comes from human coders. Yeah.
Awesome. Okay. Next question. Is there any work you are doing to baseline an individual or adjust for a detected race, gender, brightness, age, etc.?
Could you just repeat the beginning of the question again, Ashley?
Yeah, sure. So is there any work you are doing to baseline an individual or adjust for a detected race, gender, brightness, age, etc.?
Got it. Yep. So that speaks to what I was talking about before with personalization. Right now, our models do take into account individual differences. Otherwise, there's no way you'd be able to achieve the accuracy that we achieve without factoring in some contextual information. So just there, what I should contextualize there is that model that tries to baseline for the individual, we use that in our video-based model. And the reason is we believe that the only safe way to estimate what an individual's baseline is through observations of that individual. So as an example, when you look at fax coding, facial action coding system coding, which is a way of coding up individual facial expressions, when you fax code a face, you need a reference neutral image in order to accurately fax code a face, because there's changes from individual, as I mentioned, with age, you get wrinkling, where wrinkling can be a sign of someone, for example, furrowing their brow, but you don't know if their brow is furrowed until you see a neutral reference photo. That could actually just be their natural resting face. And it's not to say that people's resting faces are fully relaxed, fully neutral. Otherwise, Botox wouldn't work. In Botox, they actually kill or deactivate some muscles in the upper face in your brows that are contracting and resulting in wrinkles up there. What they do is they actually relax those. So it's because your resting face actually does involve some amount of these muscles being activated. So yeah, the immediate question is yes, our video-based models where we see more than one frame of an individual will factor in observations of that individual over a past window of time to estimate what we believe this person looks like and account for it accordingly. If you use our SDK as in the static mode to process a still image, that's going to give sort of the best guess there. So again, you'll still get good results, but not as good at picking up, for example, the subtle expressions that typically only come from being able to see person over time.
Okay, great. All right, next question. So this has a few parts to it, but the first piece is, how do visual and audio data compare in the amount of details available to sense emotions? Is one more rich than the other?
Now, this is one where I wish I had our lead speech and scientist, Tanya, here with me. I come from more of a vision background. She spearheads our audio work, but at a high level, it depends on the target. In some cases, targets may be very difficult to, as a classification problem, some targets may be very difficult to distinguish between using the face, whereas from the audio channel, you see a much easier separation. So as an example of one is, if you're really, 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 really high arousal, sometimes it could be a tough time distinguishing between the valence of that from audio. Like if you're yelling and screaming, it's hard to tell if it's from excitement or joy, or if it's from anger or fear or something else, right? At a certain point, the valence signal disappears amidst this high arousal. Whereas when you look at the face, there's a very clear distinction between someone who's extremely happy versus someone who's extremely afraid or extremely angry. But another is the example where I mentioned the context is the key. There's a classic photo you could probably find online, and it stems from a study in psychology where there's a person with this nose wrinkle, brow furrow face. And what they showed in one photo, his hand was holding up a banana peel, and in the second photo, his hand was holding up a fist. And depending on which of those two images, people would interpret that either as anger or disgust. And that showed that the identical face could be interpreted in different ways based on the context. So you actually can find that, not for all expressions, because disgust and anger can manifest in different ways, but there's sometimes overlap there. And in some of those signals, there might be a cleaner separation by analyzing the audio. So ultimately, I think the overall takeaway message is that, we believe that the two are extremely important, and ultimately merging them together into a single will have to be done to produce a single estimate. Now, when you produce that single estimate, it might leverage on the audio or the face differently depending on the situation or what it is that you're trying to estimate.
Got it. Okay. So there's also like a follow-up piece to this question you might have already answered, but if there's anything you want to add, it says also people tend not to speak all of the time while cameras pick up emotions continuously. Would this make audio-based emotional AI less accurate? I'm not sure if there's anything you wanted to add.
Oh, ton to add there. So where potentially less accurate, I would actually, in all due respect, completely disagree with that. So it depends on what it is you're doing. When you're driving a car, if you're driving by yourself, certainly your spontaneous reactions will manifest on your face more. People don't walk around saying, I feel angry right now, I didn't like that song, when there's no one else in the car. But that's actually not to say that there is self-talk. People do curse at themselves, swear at themselves, extremely evocative events will trigger you to self-talk. That is something we do, and that's something that is possible for the audio stream to pick up on and could be very salient, discriminative. But then there's another use case when you're having a conversation with someone. Either this could be interacting with an AVR system, a voice-activated audio system. There you're speaking. If you're having a conversation with someone in the car, either over the phone or another occupant in the car, then again, that conversation becomes really important. Now, where the audio cues come in is that the facial actions get engaged, especially the mouth facial actions are engaged to produce sound. You can still see someone, smiling through the act of speaking, but some of the real subtlety is going to be gone from the face because they're busy using their face to create the sounds in speaking. And so there you will have to potentially rely more on the audio signal. I could see that happening. There's obviously cues in the face that are going to be really important. Your eyebrows will be used for accentuation, things like that, but that all has to come together. So is the audio less important? In a case where someone is just sitting in a vehicle by themselves, there's an opportunity for it to still augment, but where it really shines is when you have any kind of conversational use case, either two people interacting, you interacting with a voice-activated system. I personally have a voice assistant in my home and find it extremely useful, and I think that's just the direction that these kinds of interfaces are going. I'm very diligent at being hands-free when I'm in my device, and so I do everything using the voice when I'm in my car.
Okay. Next question. In the Affectiva video emotion analysis, how do you indicate a neutral emotion in emotion score?
Sure. So one of the things we do, and I didn't mention this explicitly and could have, is that we treat the emotion estimation, we allow for that not all emotional states are mutually exclusive. Actually, all of our emotional states that we detect are independent, and therefore they're all jointly trained and produced simultaneously. But for those well-versed in machine learning, it's not fed through a softmax. Each target is actually trained independently and can be evaluated independently. So you can actually have 100% joy, that joy is present, and 100% that surprise is present to indicate that they're expressing both joy and surprise simultaneously. The other, for those listening in that are sort of where the other approach you could treat this is to have neutral be an explicit class. You have to choose between neutral or joy or surprise or anger. You have to force that choice. and therefore you have to have neutral as in a class explicitly, because there is no room for saying, here's a class that I don't yet recognize, right? You force it into one of the bins, and because of that, you might need to create an extra class, which is unknown, which is a face I've never seen before, or an expression I don't know how to interpret, because it's not neutral. It's not a neutral, relaxed face. It's not an emotional face. So yeah, so there we don't have, how do you detect a neutral face? It would just be the absence of all the other emotional states. Now, what's that to say? Is that neutral, or is that some other emotional state we don't detect? It could be either of those, but ultimately that's the same as the neutral case. We don't have an explicit, this person's completely relaxed, neutral classifier.
Right. Okay, well, that's just about all we have time for this event. So I want to thank you, Jay, for your time today, and for all of you joining us and for your questions. We tried to answer as many as we could for coming up at the top of the hour here. But it was an amazing webcast. I certainly hope that you guys learned a lot. I know I did. We did record today's webcast, so you should receive an email shortly with the webcast recording as well as the slides. For details on our next webcast and other upcoming events, you can follow us on social media and sign up for our monthly newsletter at affectiva.com. So thank you again, and have a great day.
And thanks a lot for the great feedback. If you want to hear more of this kind of stuff, let us know. It's been fun.
Excellent. Thank you, guys.